Hello and welcome back. This video is meant to accompany the notes for AP Physics 2 on electric charge, force and energy, and electric field. Please feel free to stop, pause, and rewind the video as necessary. Let's begin. Section 14.1, Electrostatic Interactions. How many types of electric charges are there? What are their names? There are essentially two different types of electric charges, positive charges and negative charges. Now, if we look at basic atomic structure, positive charges, well, those would be protons found in a positively charged nucleus. Negative charges would be the negatively charged electrons that surround the nucleus. But for now, we can just refer to them as positive and negative charges. Does any object have all of one type of charge? How can an object have a charge? Well, essentially, all objects are electrically neutral because all objects are made of atoms, and all atoms originally contain equal number of protons and electrons. Now, an object can become charged by gaining or lose negative charges. How can charges either attract or repel? Well, the general rule of thumb for electrostatic interactions is that opposite charges attract each other while like charges repel each other. Can an object attract an uncharged object? How or why not? Well, the simple answer is yes. A charged object can attract an uncharged object because the charged object causes a rearrangement of negative charges within the neutral or uncharged object, thus creating an attraction between the two. Let's take a look at this simple example of a balloon, which is an insulating material, and a wall, which is another insulating material. Now, what you see here is a balloon that we can rub against this wool sweater and gain a net negative charge, meaning there's more negative charges than there are positive charges on the balloon. And the sweater has a net positive charge because we have removed the negative charges from the sweater. Now, the sweater is no longer my interest anymore. The wall is. The negatively charged balloon can shift the negative charges in the wall away from the outer edge, making the outer edge of the wall appear relatively positive. You can even take the balloon in dry conditions, stick the wall to the balloon. The balloon sticks to the wall because of this electrostatic separation. Now, of course, once you take it away, everything shifts back to normal. But this rearrangement of charges can happen when we take a charged object to a neutral or uncharged object. Section 14.2, Explanation for electrostatic interactions. Is the attraction or repulsion of electric charges the same as the attraction or repulsion of magnetic poles? Well, positive and negative charges can attract a magnet. They're very similar. In other words, positive charges attract negative charges in the same way that north poles attract south poles. So there are some similarities there. Now, a positive and negative charge can attract a magnet. We would have to make the assumption that the magnet behaves like an uncharged piece of metal, like the wall that we saw only in metal form, and thus would be subject to the rearrangement of negative charges for electrostatic interaction with the charged object. Explain the fluid model of electric charge. Well, the fluid model was proposed as a way of describing the interaction between charged objects, and it was thought to be an electric fluid found in all objects that had the ability to transfer from one object to another, as opposed to the particle model of electric charges, which proposes that particles that comprise and make up matter carry the electric charge and not a weightless fluid. What do we call an atom with a net electric charge? How can an atom become positive or negative? Well, an atom that has a negative charge, a net electrical charge on it, is called an ion. To become positive, you need to remove negative charges from that atom. To become a negative ion, you need to add negative charges to that ion. Section 14.3, conductors and non-conductors, dielectrics. Well, another name we can give for a non-conductor would be an insulator. An insulator is essentially a non-conductor. What makes an object a conductor? As in, what do charges do in a conductor? What types of materials are the best conductors? Well, simply said, conductors allow for the free movement of electrons. Electrons have the ability to essentially move throughout from atom to atom within a conducting source. Metals are, of course, good example of conductors. Gold, copper, which is why those are used for wires. Copper is very cheap, which is why it's the most common form, and silver even. But metals are very good examples of conducting materials. Electrons have their way of making their way through a metal source. All you have to do is hook up a voltage source to a piece of metal, and then the electrons will then want to move. They have to be given some reason to move. They don't want to move on their own, but given some voltage source applied to that piece of metal, they will want to move from one area to another area. What makes an object an insulator, which is also known as a non-conductor or dielectric? What types of materials are the best insulators? Well, insulators, by contrast, do not have free electrons being able to move around on the inside. Examples of insulators would be plastic, glass, wood, other non-metallic materials. Another thing to mention about conductors is electrons, which we're going to denote as with the sign E minus. Electrons are found around the outside of conductors. So if you have a solid conducting material, the electrons are going to disperse themselves around the outside. They want to get far apart from each other as possible. Explain polarization and electric dipoles. Polarization is the process resulting from the separation of negative and positive charges, like we saw with the animation of the balloon and the wall. The wall became polarized because the negatively charged balloon repelled the negative charges further inside the wall, separating the negatively charged inside of the wall from the positively charged surface of the wall. These separated regions are called electric dipoles. Name a dipole molecule that you are very familiar with. Explain an experiment and observation that shows that this material is a dipole molecule. Well, one familiar type of molecule that fits this description would, of course, be a water molecule. The hydrogen end of a water molecule is relatively slightly positive, and the oxygen end is slightly negative. This gives water a slight charge difference from one side to the other. And if you take a charged object and you run it, you bring it near, say like you take a charged PVC pipe, or you run a comb through your hair, or you take a charged piece of styrofoam and you bring it near a stream of running water, you can get that stream of running water to bend one way or the other, essentially attracting or repelling itself from the stream of water. Explain how an electroscope works. Now in this part, we're going to explain how it works. In class, we're going to draw up and illustrate how it works. First, the explanation. An electroscope consists of a metal ball connected to a metal rod, which is then connected to two metal foil leaves, usually aluminum foil or gold foil, very thin foil leaves. The whole purpose of those leaves is to be able to separate from each other. The whole apparatus is insulated by air and enclosed in glass to keep the charges essentially able to move on the metal ball, the metal rod, and the metal foil leaves only. The electroscope works to use the movement of free electrons within those metal conductors so that you can see evidence of electrostatic interaction, specifically in the foil leaves. We will illustrate this later on. Is the human body a conductor or an insulator? What evidence do you have for this assertion? The human body is a conductor. Well, we know this because if a person has no heartbeat or an irregular heartbeat, we can use what's called a defibrillator to stop the heart rhythm and reestablish another one. And we do that by putting one probe above the right hand side of a person's torso and the other probe, the other part of it on the lower left side of the person's abdomen. And the electric current essentially runs across a person's heart. We also know this, of course, because a person who comes in contact with a certain amount of electric current can become electrocuted because that electric current can pass through the body. Now, we will get into electrical resistance at a later time, and we do find out that the human body, especially if it's dry, is a very high resistance to electric current. But nonetheless, the human body is still a conductor of electric charge. What does it mean to be ground? Well, essentially, think of grounding as a way for a place for electrons to go, a very large empty space, not necessarily empty space, but a large space for electrons to gather where they don't really care about the electrons that are coming. There's no reason to repel these electrons. It's just an infinite holding tank of electrons. For instance, your car battery, the negative end of your car battery, is connected to the piece of metal frame of the car. So the piece of metal frame represents a very large depository, a very large place for electrons to be deposited into. Or it could be a metal pipe or a piece of wire that's actually connected to the ground, where the earth represents that as well. Grounding is really important for electric appliances and is seen with electric appliances that have the third middle plug. That third plug is the grounding plug and helps to avoid those electric shocks. More about that later. Explain how objects can discharge due to the presence of moisture in the air. Well, moisture in the air contains water vapor, and as we discussed earlier, water is a slightly charged molecule, meaning the water vapor in the air has the ability to pull and remove electrons from a charged object slowly over time. That is how an object can simply discharge itself due to the moisture in the air. It's the other reason why, if there's enough humidity in the air or enough moisture in the air, many static electricity type of experiments and demonstrations just simply will not work. What does it mean to say that a charge is quantized? Well, quantized means that charging an object happens in specific increments, not continuously charging. Those specific increments were figured out and determined as the charge of an electron, which is about 1.6 times 10 to the negative 19 coulombs. We'll discuss that one a little bit more in application. Section 14.4, Coulomb's force law. In this table, we see data from 10 different experiments where charge 1 has applied a force on charge 2 where the charges, charge 1 and charge 2, are separated by a distance r. So each part of this has a certain variable. The second column represents charge 1, the third column represents charge 2, the fourth column is the distance between the charges, and the force of interaction between those two charges is seen with the last column. We can see with row number 1, that is the original baseline set of data, where 1 unit of charge interacts with 1 unit of charge 1 unit distance away to create 1 unit of force. Now for experiments 2 and 3, you can see we are just adjusting only charge 1, and it only affects the force from charge 1 and charge 2. This is a controlled experiment, so we leave charge 2 and the distance alone. You can see that experiments 4 and 5, we are only changing charge 2, leaving charge 1 alone and the distance alone. Experiments 6 and 7, we appear to be changing charge 1 and charge 2 together. Experiments 8, 9, and 10, we are only changing the relative distance between the charges. Let's talk about the results. Which experiment trials should be used to determine the relationship between force and charge 1? Fill in the table below with these experimental trials. What type of relationship is there between force and charge 1? Well, the experiment that specifically focuses on charge 1 would be the baseline experiment of 1, but also 2 and 3. And we can see that charge 1 was cut in half for experiment 2, and then cut in fourth for experiment 3. And we saw from the results in the data table that the force of charge 1 on 2 also cut in half when the charge cut in half, and the force cut by 4 when the charge was cut by 4. Which experiment trials should be used to determine the relationship between force and charge 2? Fill in the table below with those experiment trials. What type of relationship is found with force and charge 1? Well, there we're looking at experiment 1 again for the baseline data, but then also experiments 4 and 5, where we can see charge 2 is changed. Creates the exact same type of relationship as we saw in the previous example. And in both of those cases, there is a direct relationship between the charge and the amount of force applied. Now, when it comes to changing the distance, we can see that with the base experiment 1 and experiments 8, 9, and 10, where we are making the distance doubled and then tripled and then 4 times farther. We can see that the force goes down when we double it by a factor of 1/4, when we triple it by a factor of 1/9, and when we quadruple it, a factor of 1/16, which means the force varies with the inverse square of the distance. Well, what is Coulomb's law? Coulomb's law is a mathematical relationship. It's a mathematical expression that shows the interaction of charge 1 exerting a force on charge 2 separated by distance r. F is the force measured in newtons. Q1 and Q2 are the charges respectively, 1 and 2, measured in coulombs, noted with a capital C. R is the unit of distance. R is the distance between the charges, measured in meters. And K is the charge constant, which is approximately 9 times 10 to the 9 Newton meter squared per Coulomb squared. In the hydrogen atom, the proton and electron are separated by about 10 times 10 to the negative 10, 1 times 10 to the negative 10 meters. That's approximately what's called 1 angstrom. Calculate the electric force of attraction and the gravitational force of attraction between these two particles. Show your work in the space below. Explain any additional information you need to obtain these forces and show the basic equations and plugins. Well, we need to know the charges for a proton and electron, and that's about 1.6 times 10 to the negative 19 coulombs. It's the same for both. We also need to know the relative masses. the approximate masses for protons and electrons. The approximate mass of a proton is about 1.67 times 10 to the negative 27 kilograms, whereas the mass of an electron is approximately 9.11 times 10 to the negative 31 kilograms. Let's take a look at the calculations. Find the electric force between a proton and electron. The equation we would use is the one above, the Coulomb's law equation, K times Q1 times Q2 divided by R squared. When we plug in the numbers, we get an electric force of about 2.304 times 10 to the negative 9 newtons. Finding the gravitational force between those same objects, we use the equation gravitational force is equal to G times M1 times M2 divided by R squared, where M1 and M2 would be the mass of a proton and the mass of an electron. Filling in those numbers, we get an approximate gravitational force of about 1.015 times 10 to the negative 47 newtons. As you can see, an electric force is clearly many times larger than a gravitational force. And if we looked at them and divided the two, specifically, we can see that an electric force is 2.27 times 10 to the 39 times larger than the gravitational force between a proton and an electron. Section 5.1, a model of the mechanism for electrostatic interactions. Explain what an electric field is. Well, an electric field is like an electric disturbance that's found around a charged object, and this electric disturbance can thus create and exert a force on other charged objects nearby. The closer you are to a charge, the more disturbance you experience, thus the higher the electric field. What causes an electric field is the differences in voltage from where the charge is located to some other point a distance away. The greater the distance in voltage, the stronger the resulting electric field will be. The magnitude of an electric field is directly related to that charge that's causing the disturbance and inversely related to the square of the distance from that charge to some test point region a distance away. More on the electric field magnitude in a little bit. The direction of electric field is defined as going from positive, a region from positive to negative. The positive region is a region of high electric potential. The word potential is synonymous with voltage. So a region of high potential to a region of low potential is how electric field lines are always drawn. The equation for electric field is E equals K times Q, the charge that's causing the disturbance, divided by R squared, where a capital E is the variable used for electric field, and the units can either be newtons per coulomb or volts per meter. A gravitational field, by contrast, would be a disturbance in the space-time around a mass. Think of outer space as one giant trampoline, or bed sheet, if you will. The larger the mass, the larger the distortion of space-time, the more other masses would want to curve around that large mass and thus be attracted to it. What causes a gravitational field are the sizes of the masses themselves. The greater the mass, the greater distortion of space-time around the mass, thus the greater attraction and the greater the gravitational force of attraction to other masses nearby. The magnitude of a gravitational field is directly related to the mass and also inversely related to the square of the distance from that mass to some test point region in space. Gravitational field lines are always drawn towards the center of a mass. And the equation for it is little g, which is the variable for the acceleration due to gravity. In this case, it's also the magnitude of the gravitational field of attraction. Little g is equal to big G, which is the gravity constant of approximately 6.67 times 10 to the negative 11, times m, which is the mass creating the disturbance in the space-time around, divided by r squared. The basic equation for electric field is E equals kq over r squared. Now, sometimes a capital Q will be used, sometimes a lowercase q will be used. Generally speaking, lowercase q's are usually used for test charges or small charges, whereas capital Q is usually represented for some point charge that has a larger value of charge associated with it. But honestly, we will go back and forth using little q and big Q. It really doesn't matter. The basic equation for gravitational field is very similar, only instead of kq over r squared, it's gm over r squared. And when multiple masses or charges are involved, we simply need to add the vector sums of these gravitational fields or electric fields. Try filling this out, pause the video, and then go over it with me as I reveal each of the blanks below. The gravitational field near the Earth's surface is 10 newtons per kilogram. Remember, the unit for G could either be meters per second squared, because it does represent the acceleration due to gravity near the Earth's surface, but it also represents newtons per kilogram as well. This means that every kilogram of mass in a gravitational field receives 10 newtons of attractive force, because gravity only attracts. Well, similarly, an electric field near an Earth's surface is 100 newtons per coulomb. This means that every coulomb of charge in this electric field receives 100 newtons of attractive or repulsive force. So the difference, of course, would be gravitational fields only attract masses, whereas electric fields can attract or repel depending on what the charge that you place in an electric field. If I place a negative charge in an electric field, well, then a negative charge goes against the field, whereas a positive charge goes with the direction of the field. More on that later when we apply our work. I hope you found this useful. Please pause and rewind as needed. Bye-bye.